See, do we show? There it goes. Recording started. Awesome. And okay. So, folks, welcome to the January meeting of the Northwest C++ Users Group. First off, I'd like to thank Microsoft for sponsoring both the Reactor Room and our Microsoft Teams support. We also would like to make sure everybody knows Microsoft does have a code of conduct. We've adopted it for this group as well. It's pretty much just be nice and friendly to each other and respect. So. Okay.
Is the mic on?
Can folks hear me okay?
Ben, give a thumbs up if you can hear Lloyd.
Awesome. Thanks, Ben.
That's me.
Sure thing. Did you not hear me when I spoke up a moment ago? I had
Oh, we
myself
did.
muted, but okay.
Okay, and I'm looking for presenters for 2025. August and on is still open. In July, we are going to, we're still kind of getting the pieces of this together, but we're going to try to do a group session with the rest, kind of a crossover, and it'll be a language panel. So stay tuned for that. We'll probably be pestering people to maybe talk specifically on certain languages or something.
Don't worry, you've never pestered me, Lloyd.
Ever there was a side eye.
I was trying to be subtle. Not. Okay. Something else we've just started recently. After this meeting, folks, if you would like to, there's just kind of an informal get-together at the Red Robin on 148th and 24th Street. Just kind of hang out and talk programming stuff. Okay, with that, I'm going to hand it over to Walter for our feature presentation tonight. And give us a second to switch things over. This was a USB-C. Well, theoretically, it should just work.
It was working before.
Nope, nope, it's getting there. The Mac is recognizing. There it goes.
Aha.
It does just work. It's just a hair slow. Okay.
All right, I'm going to talk about the black part of code generation. How many of you have written a code generator before? Worked on one?
How complicated is it?
So that'll be interesting because not many people deal with code generators. Now these numbers I just made up. Full disclosure, but I think they're roughly accurate. I mean, how many books on lexing do you see? Well, there are 1,000 books on how to write a lexer. Maybe 100 books on how to write a parser, maybe 10 books on semantics, a very rare book on optimizing, and there's just nothing on code generator. So that's the state of code generator information available. An empty wilderness. So if you're going to do anything with a code generator, you're going to have to rely on basically looking for the lore, looking for articles, papers, reading CPU specifications, which are, gloriously easy to read. Dogged persistence. Godbolt.org is a miracle for anyone trying to understand code generation. Even though it doesn't tell you what's happening, you can try various things, run it through, and push the cow through the hamburger. I mean, the grinding machine, and the hamburger comes out, and you can sort of make an inference about it. And well, me. Okay. I wrote this code generator originally back in the 80s. This presentation will be about that code generator because I know next to nothing about anybody else's code generator. I don't know how close they are or how diverse they are. I don't know anything about them. And what I wrote is not derived from anybody else's code generator. There are no ancestors to it. And it started as an 8088 16-bit code generator. And shockingly enough, it managed to survive a transition to 32 bits and then survive another transition to 64 bits. And then another transition to SIMD. And I'm currently working on an ARC64 version of the same thing. So I'm actually rather shocked because each time there's a new revolution in the CPUs, I thought, well, that's the end of the line for my code generator. But I get to thinking about it and I figure out how to make it work. The source code is all boost license, which means anybody can use it for whatever reason they want to, and they don't have to get permission or nothing. So you can't understand a code generator without understanding its data structures. So that's kind of what we're going to focus on. So let's start out with a simple stuff, an expression x equals y plus 3. And we think of it as a binary tree. And we all know binary trees, so everybody should have no difficulty at all with this. Internal representation of expressions are binary trees. And I seem to have lost the bottom of the slide.
That's probably a PDF thing. That's not a Mac thing.
That thing can.
No, it's a touch.
What?
Yeah. You're getting the full page, but it's
Oh,
PDF, whatever, when it converted to PDF, it printed off the bottom.
well, the PDF file is correct. Anyhow, the node has an element for the operator, its type, various flags for various kinds of things.
There we go. 2 fingers.
Oh, 2 fingers. Okay.
Yeah.
Thank you.
Yeah.
E flags are, various characteristics. The bit flags form. Ecount and ecom sub are there to manage common sub-expressions. And then we have the union. And the node can hold a constant, a variable, or a left and a right tree. Okay, and let's take this trivial function. Sometimes people complain about my trivial functions, but I do the trivial functions because everybody can understand them instantly. If I showed a screen full of code, everybody just tunes out. I know I tune out when anybody shows me a slide that's full of code. So this is on purpose. The functions are trivial. The compiler has a --b switch, which will dump the trees that it sees, the backend. And if we want full disclosure, it will dump the contents of that node, or the elem structure I showed previously. So here's the comma operator, which divides the 2 things, and we have x equals y plus 3, and then x for the return value. So although it looks like a row of numbers, and of course, nobody understands these constant pointer values, but it's really quite straightforward. Expressions are only the part of the problem. You have statements, and statements are connected by edges. And we call that a block. And we have the kind of block it is. And this is what it does when it finishes executing the code in the block. It can go to another block. It can go to another block if the result of the expression is true. It can do a return from the function or return the value of the block as the return from the function. And here we have the expression tree for this block. Each block has a list of successors, which are the edges going outward. And then you have The next one is a linked list of these blocks is formed for each function. And here's the code generated for it. Now, if you look at the actual source scope, there are many more members in there, but I boiled this down to just the basics of how it works. So let's take this simple function, which is pop count. And who doesn't know what pop count does? So I don't have to explain it to anyone. It's a standard function to count the number of bits in an integer. And it has some interesting things. It's got some declarations and it's got a loop in it. So this breaks down to the block structure. The first block is n equals 0, and its successor is b2, and this is a goto, so it goes there. And if true, it goes to b3. If false, it goes to b5. And evaluates x, that's the while x. Our third block is this statement, n plus equals x plus 1, and it goes to its successor, b4 there. B4 does the right shift, and then the last statement is return this expression, which is simply n. So everyone's nodding their head. This should be pretty simple. Okay, I tried to make it as simple as I could. So then we generate code into this code structure, and it's very similar to the blocks. We have a pointer to the list of instructions for it, or the next one, because this forms a linked list of instructions. Well, you look at the assembly dump of your function, what does it look like? It looks like a list of instructions. So here's the data structure for it. You have the next instruction, flags for, the usual bookkeeping nonsense. The operator, the effective address. Okay, who knows what the effective address is? So no x86 programmers here?
No, I'm confused now because your variable name is actually an opcode for the x86 load effective address. LEE, that's an opcode recognized by x86.
Well,
So when you were talking about effective address, I had a problem mapping the semantics.
all right. Well, here's what an x86 instruction looks like. You have your opcode, and you have your effective address, and that is the mod bridge RM byte.
That's what you.
Anybody remember the mod bridge RM byte for the old? Yeah. You guys have all moved on to the ARM64. So that's what the EA is. It's called the effective address. And so you have the opcode, which would be like, the AND opcode, and then the EA. And the EA covers, is it a register, AX, or is it indexed by AX, or is it indexed by AX plus, SI or something like that. That's all encoded into the effective address.
So essentially it encodes the operand.
No, it controls when there are two operands, or sometimes one operand. You have a register and the EA are the two operands. Sometimes the EA can simply be another register. You have the kind of operand it is, which is the FL, and you have your two operands. There. And this is another union for the various kinds of operands.
That goes with the scroll as well.
Oh, perfect.
Pretty easier.
Okay. Here's a generated code for our pop count. We have the prologue where it sets up the stack frame and stores your register variable on the stack. And here it sets X to 0. And here it compares it as a jump. That's the code generator for B2. For B3, we have the first statement in the loop, the second statement in the loop, and the jump back up to here. Move the return value in the EAX, and then the function epilogue. So this RBP here is the EA. Okay, this is the EA, and this value here goes in the first operand. So the EA encodes the addressing mode, which has a constant, and the constant goes as one of the operands. Does that make sense? Unfortunately, the EA is ridiculously complicated, and it gets more and more complicated with every iteration of the CPU. But you know, that's the cross I have to bear. Okay. As everybody know, a code generator has two switches. It has the optimized build and the unoptimized build for speed. Well, it turns out that you can't really do an unoptimized build. The code generation is horrifically bad. You have to have some optimizations in there to make it even usable. So here's an example of these simple optimizations it does. If I have A plus B plus C plus D, if I rewrite it to this form, it uses one less register. Everybody see why it needs one less register? Okay, because these two are computed, or this is computed, stored in a register. This is computed, stored in a register. Then the two registers are summed. Okay, and this one, compute, store in a register. Add C to the register, add D to the registers. One less register. And when like the x86 has 6 registers, this is an extremely crucial optimization. Okay, one less register. So why is a triangular wheel better than a square wheel?
Less bumps.
One less bump. There you go. I think that every time I see one less register, it's got one less bump on.
At what level can you prevent that kind of optimization occurring?
You can't.
Can I rewrite the source code to prevent that?
No. Every compiler you find will do that optimization whether you like it or not. Besides, why would you want to? There's
Addition is not strictly, computer addition is not strictly associative. It's almost associative, but not quite.
oh, you're talking about floating point.
Floating point, yeah. And in that case, you might want to control the order to be more likely to get the correct.
That is
the
a
answer
really great
you
point.
want.
With floating point math, the order matters. With integer math, it does not. And it doesn't do that optimization for floating point. You know, you're absolutely right. Common sub-expressions, it turns out that if you don't, common sub-expressions are so common that you can't write a code generator that doesn't do common sub-expressions because it will be horrific. So here we have two common sub-expressions. And it walks the tree, keeping a table of all the nodes I've seen. And if it finds a match, it goes and snips this thing off and runs a little. That makes it not really a binary tree anymore. So this is done as the last step before it actually goes to generating code for it, because none of the other optimizations will work because they will get all fouled up with that.
Mhm.
And those two counters, the ecom sub and the ecount, are the reference counting mechanism. So everybody knows how reference counting works. So a reference counts a common sub expression. So when it's going through the code generator, if the two numbers are the same, it knows I need to generate this common sub expression. And if the two numbers are different, that means I can reuse an existing result. So that's how that's kept track of.
Yeah.
And heaven help me if anything in the code screws up that count, because everything mysteriously fails.
So you're also keeping track somehow of aliasing and side effects so that
Oh, yeah.
B is the same B and it's within the same scope and
Yeah.
we don't have a inner scope B or anything like that.
If this was B++, then that's not a common subexpression.
Or if it's still B, but in an inner scope somewhere. But it takes a completely different variable representation inside the.
Okay, if two variables have the same name to the front end, they don't in the back end. Everything has a unique name, so there are no problems with having two variables representing the same address.
So the common sub expression has to be leaf expression, because if anything else acts on B, then. Or
Well,
something like that.
it's treated as a leaf, but it's actually not. Because the code generator runs in a loop, so it can't destroy the trees. It generates the code and then it reconstructs the trees back the way they originally were for another try through the code generator. And I'll get into why it does this in the that's a bit of an ugly part about the code generator. Okay. One thing about the x86 registers is every register has a different purpose. And they all overlap in a completely unpredictable, crazy mishmash way. So, like if I want to use a multiply instruction, I've got to use AX. But if I want to just add, I can use any of the instructions. And, if I want to use the string instructions, I've got to use SI and DI. So I needed a way to tell which set of registers are useful for, or do I need to generate this piece of code? Came up with the idea of register mass. Okay, so over time, the register mass got wider and wider and wider as Intel keeps adding more registers to it. And I get to the point worried, am I ever going to be able to expand this? Because the whole thing relies on register mass, and when they're too big, it's unworkable. So I made it an alias is a type def. So I made it a specific type def, and I carefully try to adhere to that, because if I change the size of that and it doesn't line up with everything falls apart. So we got all regs, which is a misnomer because it's the integer registers. But it turns out on the 8088, the integer registers were the only registers. That's why it's called all regs. Later on, it added FP regs for floating point, and then the XMM regs is a mask for all the XMMs. And we have variables like registers preserved by a function and mask for registers we like to save. So it turns out that a lot of the code generation operations runs off of bit mass. And it turns out that this design makes for a very, very fast code generator. I've never had speed problems with it. And it always has been faster than anybody else's. And part of that is the beauty of bitmass. There we go. Yay, effective address. Effective address consists of an offset, base register plus an offset, base plus index times scale plus an offset. Turns out that the ARCH64 does not have a concept of an effective address, which for a while there, I thought I would never get the code generator to work with that, and I finally figured out a way. It took me a while. Did we show this before?
Yeah, I think you jumped back.
No, I wonder what happened. Oh, well, we'll just. Okay, here's the entry point in the code of the code generation. Right func. And it sets up the symbol table, and the symbol table is a simple array. So the each variable becomes an index into the array, and that's very simple to deal with. The intermediate code optimizer, which does data flow analysis and all that, is optionally run. And when that runs, I'm not going to talk about how it works in this because that's a whole other long presentation itself, how to do data flow analysis. And its output is just in the same format. It's just a new set of trees and a new set of blocks. And then it calls CodeGen, which is the code generator. And when it's done, it shuts down the data structures and emits debug info for the function. Oh, and then it saves the results. It might be used for inlining later. So how the flow of control in the code generator, first it sets the stage. If it's optimized, it does things in a loop, generates code in depth first order. We know what depth first order is? Yeah. And then it allocates unused registers to variables. And this is done in a loop. And the reason it's done in a loop is it cannot predict what registers will be used and which will be unused until it's generated code, but it can't generate code till it knows where the registers go. So the whole thing is done in a loop. It starts with a basic thing and it allocates registers and generates code. And at the end, it looks to see if there are any free registers left. And it's not predictable because all the registers have different purposes. It's not predictable which registers will be left. So what it does is it looks to see if there are any registers left, and if so, it allocates those to variables, and then it resets the code generator and runs it again, which frequently frees up more registers, and that's why it's running in a loop. And fortunately, it always converges to a solution that does not get stuck in the loop, and usually it only takes a couple of runs through it to converge to a solution. But that's with the register. That's only if the optimization is turned on. And that is not the DFA, the depth first, or the data flow analysis, which is done the optimizer path. The data flow analysis provides data for this.
So I have a question. Let's say that there is a variable that gets used in the top half of the function, but not the bottom. Does this allocate the same register for the top half and again in the bottom half if the top half is gone out of scope?
What you're talking about is register allocation by coloring.
Okay.
Yes, it does register allocation by coloring, which is, really stupidly simple. Anybody, guess, don't have a blackboard to draw on. But basically, you have all the blocks, right? The list of blocks. Well, what does that suggest to you? It suggests to me a bit vector. So we have a bit vector, and then every time, so the optimizer gives us the bit vectors of all the symbols in the function. And then when you run the code generator and it uses the register, every time it uses a register, it marks a bit for that. It says this register has been used in this block. And so the register allocator just does bit masking. And if it finds the mask of bits used by the variable versus the mask of bits of free registers, and it goes like that. And if there's no conflict, it goes, oh, in there. And also the variables are weighted with this stupid simple algorithm, which turns out to be very effective, is It just counts the number of times it's used. And if it's inside a loop, it multiplies that by 10. It counts in a 10. And if it's in a nested loop, it multiplies the counts by 100. And it turns out to be extreme, a trivial and very effective heuristic for which variables get priority in the registers. And if it's in, an unoptimized build, it just loops through the block list once, generating code in that order, does it once, bing, bang, done.
You mentioned having an optimization phase.
Yes,
Does that run completely before the code generation, or are they interleaved?
completely before the code generation. The whole thing operates on a function by function basis. Okay, so it gets a function, runs the optimizer on it, runs the code generator for it, and then it goes to the next function.
Does the optimizer recognize a common sub-expression?
At the very end, the optimizer will do a better job of common sub-expressions than the fast debug build will do. So yes, it does common sub-expressions, but it uses a different algorithm that's uses the data flow analysis to give it a better result.
So in terms of finding the common sub-expression in the example you gave earlier, is that found by the optimization phase, or is that done
It has
in the code generation?
It has actually two pieces of code that does common sub-expressions. One is for the fast mode, which is, generate code as fast as possible. And the other is for the optimized build. And for the optimized build does a better job because it's using data flow analysis than the quick and dirty one. So there are two common sub-expression optimization procedures in the compiler.
Question.
Oh,
Somebody
Yes.
has a hand up.
So, do you have any special, like handling mutually recursive definitions, or like you said, you do one definition at a time? Does it ever happen like where you're going to inline, like you have a mutually recursive definitions and you're going to inline one into the other, or anything like that?
okay. The inliner is done separately from this, but yeah, the inliner, when it's inlining something, it marks the function as it's being inlined. And if it encounters the function again, it says, oh, I'm already being inlined, so I'm not going to inline it again. So that's how it stops the recursive inline expansion and mutually recursive expansions. It just sets a flag saying, oh, I'm being inlined in process, don't inline me again while that bit is set.
Okay.
Yep. So it's a very simple and effective way to deal with that. Okay. The next thing it does after it's generated code is it figures out the locations of local variables, which means they're stack offsets. And now that it has all the variables and the code it can generate and the registers used, it can generate function prologue. The function prologue does things like, moves the variables that were passed on the stack or in a register into this stack or the register that they're supposed to go into. And saves registers that need to be saved because it knows which registers are used. Generates the function epilogue, which then restores the registers that were destroyed. And then there's another pass that assigns addresses in the generate code because you can't tell what the addresses are until after you generate it. And
Looks like an alert. Yeah, I don't know why though.
oh, thank you. You're a master of this. Everybody heard of people optimizers? Everybody's heard of people optimizers. People optimizers is after you've generated code, you look at the sequence of code, and sometimes instruction pairs can be replaced with a simpler instruction. Or sometimes a triple of instructions can be replaced with a single instruction. That doesn't really happen the way DMD generates code, but it turns out that there are many encodings of the same instruction in the Intel mass of a complicated CPU. So what the pinhole, I needed something smaller than peephole, so it's the pinhole optimizer, and it optimizes an instruction itself. For example, you can have a branch that has an 8-bit offset, or a branch with a 16-bit offset, or a branch with a 32-bit offset. And what the code generator does, in order to simplify it, always generates the 32-bit offset, and then the pinhole optimizer goes in, replaces it with the 8-bit one. And you also have instructions where this shorter instruction uses the AX register implicitly. The longer instruction uses an EA addressing mode for it. So this looks for the special AX instructions and then swaps that out. And of course, that shrinks the size of the code. So then you've got to optimize the jumps. And of course, optimizing the jumps can introduce more possibilities of optimizing jumps. So you got to do that until it settles down. And generate the switch tables and then emit the generated code. Why is that jumping back? Oh, I know why. Okay, so that's a general flow of control. And it generates, how it works is the expression nodes have an operator on it. And the operator is an enum, and there may be 100 operators on it, and one for each kind of operation. So how the code generator works is it has a table indexed by the operator number, which generates code for that element node. And so here's the first part of it. Add instruction, multiply instruction, and instructor minus not complement conditional, and then the address of the code generation function in it. So you might think, why in an advanced language are you writing code like that? But it's very old code and it works fine. And element nodes are, this is a repeat it was before. It could be a constant, result of another element node, address of an L value, or the addition here of the common subexpression. And I talked about you create it or you reuse it. And an L value can be a variable or an indirection. An indirection would be like star P. And CD-COM, this handles the complementary value and is one of the simplest code generation functions. So that's why I picked it. And we pass into it the global state. It used to be use global variables, and global variables are, a horrible sin in modern programming. So now it has an extra parameter, which is the state of the code generator. Code builder is a type that you feed instructions to, and it puts them in its secret data structure. The element node, and here's a register mask of, it's an input and an output. You pass it a mask of registers that you want the result of this to be in one of those registers in your mask. And then when it returns the actual register it picked. And an endless source of bugs is in getting that wrong somewhere. Okay, how it works is it gets the type, the size, the operand size, Rex, every know what the Rex byte is? And that's the byte that says, I think you got 64-bit operands here instead of 32-bit operands. So my unhappiness at the complexity of that, I always call it the wretch. The wretch byte. It's another prefix byte. And I create a mask of the possible regs that I want to evaluate the results in. You notice if the size is 1, I pick byte regs. Registers that you can do byte operations with, or all available registers. And my return registers are the registers I want and the possible registers that I can put the result in. Okay. So the possible registers would be the byte registers or all registers, depending on the size. And that doesn't always work. So if it's 0, I go, let's just go with the possible regs and see if we can make that work anyway. And then we generate code for its operand there. And now we know that the registers it came back in, and we mark the registers as destroyed. So remember when I was talking about earlier, there's a mask of which registers are used? Well, that's the genesis of that. And if the size is less than will fit in 1 register, we figure out which register it is. Otherwise, we grab the most significant register.
Mike's got a question.
Yes, Mike.
Yeah, I think you answered.
Oh, okay. Well, that was easy.
Nope.
And here's the operand we're picking. If it's a byte operand, it's F6. If it's not, it's an F7. And genregs actually generates the not reg instruction and sends it to the CDB, which is the code builder. And then we do this horrible thing called an OR retch, which takes the retch and attaches it to the last instruction.
I've got a question here. I'm getting the impression, so x86 has got an enormous number of operand instructions.
You have no idea how many.
More than fit in my brain. But I'm getting the impression you're actually using a fairly small subset of that and using it fairly effectively. Is that a proper mindset? Okay.
Yeah. Oh, well, I'm nodding yes for those who don't see me. Yeah, it does use the full instruction set. But there are only so many instructions with the not. So
Oh, no, yeah.
that's why this is the simplest one. It doesn't have 100 instructions for the not.
Right. No, I'm saying not just this specific example, but more holistically. It's much more strategic about which operand it's using.
Yeah. Some of the more complex operands can be, hundreds and hundreds of lines of special cases,
Mm-hmm.
or maybe even 1,000 lines of special cases. It's all special cases.
Yeah.
I thought it would be better with the ARM64 because it's supposed to be regular instruction set. That was a bitter disappointment. It is not a regular instruction set. It's another giant mess, but in a completely orthogonal way. Okay, special case for the 64-bit code generation. Because the way it deals with byte registers is wacky. And the size, if the operand fits in 2 registers, then it's got to deal with the least significant register, generate code for that. And of course, remember early up on there, it said, we failed to pick a register that there weren't any registers available. So what happens down here is these are sometimes in the wrong registers, and then the fixed result looks at the mask here and puts it in the right result. The glorious register allocator, which I managed to get it all into one file. Optimizer computes the live range of each variable. Bit vector is the basic blocks with a bit step for each block a variable is live in. I tried to extend that to the basic block or the expression nodes, extend the bit vector, and it actually didn't really improve the register allocator, which was a big disappointment for me because I thought by having a more fine-grained register allocator, it would do a better job, but it didn't. So, I reverted all that. And the code generator sets a bit for each register used in the block. The variable is mapped to a register. If that register is not used in any of the blocks, the variable is live in. And again, that's just simply bit masking. When you can reduce the problem down to bit mask, everything just flies in the computer. It's very fast. It's done in a loop until it converges on a solution. So to finish things up, we write the code bytes to a buffer. Everybody know what a fix-up is? Okay. When you generate code and you have, let's say, an address of a variable, you don't know what the address of the variable is. So if it's like, extern int x, well, you don't have the address of x. There has to be what's called a fix-up record generated for it. Whereas you're telling the linker, in this location, the linker needs to patch it to be where X actually is, because this is not known until the linker is synced. But there's another aspect of the fix-ups is even the linker doesn't really know where it is. It's the loader knows where it is. So you have these also fix-up records in the executable that inform the loader of where to patch it. You could also call them just patches.
Mike had his hand up. I don't know.
Mike.
Yeah, so this is back on register allocation. So
Uh-huh.
like if you run out of registers, and then I guess stuff is just stored on the stack, right? And it is loaded if you need it or whatever.
If you run out of registers, things get shoved onto the stack.
They do what?
Well, if you run out of registers, you have to put things on the stack.
Yep.
It's not just the variables that are allocated in the stack frame. It's common sub-expressions that you run out of room keeping them around in the register. If you need temporaries for things, it'll generate them and put them in that. You have the if you want to transfer code or data to the floating point unit, you have to run it through a memory location because the integer instructions and the floating point instructions don't talk to each other. So there are more things that wind up being allocated on the stack.
Like what do you do about you have to spill stuff when you make calls too, right? Like function calls.
You make function calls, the function destroys a known set of registers. And so then the code generator, when you call a function, it looks at the registers that are going to be destroyed by that function and marks them as destroyed. And then if somebody needs a value preserved across that, it has to be stored on the stack.
Okay.
Just like if you do a multiply instruction and it destroys dx, but you can't, well, if dx is being destroyed, then whoever is relying on dx having a undamaged value needs to store dx on the stack.
Yeah. So how do you I think they call it like variable splitting. There's like the name of the variable before the register gets destroyed and then the one after, and then do you do anything like that?
It does not do variable splitting.
Okay.
Well, actually, it kind of does in the optimizer thing. Sometimes a variable will reside in a register and sometimes in a memory location. It's called spilling.
Okay.
Register spilling, that's the standard term for that. Because it's, it spills out of the register onto the stack and then you pour it back in. See, this is why nobody write books about it, because nobody actually understands it. I don't know how anybody else does this, so. Anyhow. So we write object code to the file, and for reasons that make no sense, every outfit invents their own object file format. And none of them are better than the other. They all stink. You should consult with me about how to write a object file format. So we have the Elf OBJ, which is popular on Linux boxes, the Mac OBJ, which is popular on the Apple boxes, the MS Cough. Microsoft invented their own for Windows. And then there's the one that Intel invented years ago called OMF that was on the Intel boxes for a long time.
So you made an offhand comment about how improving the register allocator. What's the metric by which you assess this register allocator is better than another one? Is it like filling up all the registers or?
Speed.
Okay.
The idea is if you get everything in the register, run faster. So, eventually, it's getting worse, So speed is, well, there are two metrics and anybody cares about with the code generator. There's speed and size, and they're often orthogonal. You get more in one direction and you lose in the other. And that's the whole point of an optimized build is, you want to go up this leg and not that leg. But the testing of it is always speed.
We got Mike that question again.
Hey, Mike.
I just forgot to.
Oh, okay. Oh, anyhow, next up is the following location, name of the symbol, offset from the symbol. Is it relative, program counter relative or absolute? And they tend to be extremely confusing. I know what I'm doing. I read the instructions. I have no idea what they mean in the instructions or the specification. So the only way to figure out is you write bits of code and you run them through GCC or VC and you look at what fix-up did they generate. And then you try to compare what they generate with what the documentation says. And the usual result is the documentation is not be trusted.
We're talking about static or dynamic, because on Linux, I know there's something really weird where if you're loading a shared object, a dynamic library, initially you have a jump. And the jump is lazy loading that thing if it's not loaded
That's
yet.
bad virtual paging.
And then the jump, no, if you're loading the DLL and if it's not there, it has all of the symbols that are unresolved have a jump, or they used to. That loads the thing, and then the jump becomes the actual calling of the function that it's now patched. Is that
That's
kind of what this refers to, or for dynamic, like for loading the shared object lazily at runtime?
okay. What you're talking about is the Windows executable format's mechanism for having relocatable code or position independent code.
I saw this on Linux, but
Okay, what it does is it adds an extra level of indirection, which is the jump table you're talking about.
but then the first time after the jump is executed and that thing is located, the jump goes away and you have the call to the actual symbol. It patches it.
Yeah, there's that, but the linker and the loader mess around with that. The
Okay.
compiler doesn't see it. But there's been a trend towards away from fixed locations in code, which is the way Intel's always worked, to have everything be program counter relative so it can be loaded anywhere. And this was kind of making that work with the Intel architecture, since it wasn't designed for that, is kind of a mess. And it often requires some wacky extra instructions to be generated that the linker recognizes, and then the linker, the code that's generated is not the code that appears in the debugger because the linker rewrote it.
I'm saving a lot of questions for the end. How
So,
do you do the debugging? How do you trace back to the source code all of the magic
well,
that's
I can
done?
answer that very simply. A code generator turns the cow into hamburger, and nobody has ever succeeded in turning hamburger back into a cow. So that's why when people,
Especially when the optimizer's on.
especially when the optimizer
Right.
is on, but yeah, you lose.
You have to keep track of all of it came from the source code most of the time. Get that.
Most of the time, you just turn off the optimizer and debug it that way. I'm sorry, nobody solved that problem. One of the fun things about being a code generator writer is the either complete lack of documentation, or the documentation is wrong, or it's incomplete as to how things work. So you spend a lot of time looking at dumps. And
Sorry, go ahead.
and and then you write your compiler and it generates this bit pattern, and you look and see, oh, it's the same bit pattern that such and such compiler generates, and then it starts to work.
Sounds like a $1 trillion cybersecurity question. Can you reverse everyone's
So
thumbs?
this is why I get paid the big bucks, which is $0. We give everything away.
So the same thing for generating the code for a signal interrupt handler. That's called from a kernel that needs to have some weird, what's that called?
The kernel fix-ups are different from the regular fix-ups. So I have that.
That's a different talk, yeah.
Yeah. I found that out the hard way. Why would they be different? I don't know.
The same thing, you have to go through dumps and see what GCC does and replicate.
Yeah, that's the only way to do it, really.
Oh,
I mean, I read the specification for the object file format. You cannot build anything based on those specifications. You have to actually write pieces of code, compile them, and the first thing I do is I write a dumper, which dumps the file format or the object files in a format that I can recognize. And people go, well, why don't you just use the Linux dumper or the Microsoft dumper? And the reason is you don't learn anything by running their dumper. You learn it by writing a dumper yourself, and that tells you the intricacies, at least, of how the thing is laid out and connected, and all the block sections are, and all that. That's an enormous aid to do that. Like if you really want to learn how to write assembler code, write a disassembler, which has worked for me. That's the first thing I did was learning the ARM64 instruction set. Was I wrote a disassembler for it. And then when I generate code, I then disassemble the code with my disassembler and see if they come out the same thing. And then I know I'm on the right track. So it provides a fabulous debugging tool. Of course, every design has its limits. You know about the H registers on the x86? Well, they're not used. The code generator doesn't use them because it doesn't really fit into my bitmask strategy. So they're not independent registers. You can't have different byte variables in the H registers.
I'll have EAX and AH and RAX.
Yeah, you cannot have AH and AL as independent variables. It just don't. 64 bits means no more registers can fit in them, and you think that 64 registers will be enough for anyone. But as we all know, that is no longer the case. So, at least for some of the code generator, it just doesn't do anything with the registers beyond 64. You cannot have loops in the expression tree because it limits inlining, and it results in limiting the inlining possibilities. The expression tree has to be evaluated, but it just has no loops in it. I've considered adding loops in it for decades and never got around to it, and kind of seriously doubt that would actually help anything. The x87 does not fit into this model. So it is a giant kludge with its own code generator that is different from the rest of it.
Why do you, who still cares about coprocessor?
Well, the 32-bit x86 is still coprocessor. So why is the code generator so complicated if I have such a simple presentation? This presentation isn't going to teach you how to write a code generator. It's just a, the top overview of the general flow. 8-bit microprocessors. I first tried to learn assembly language on a PDP-10, which had a zillion instructions, and I was totally lost. And then I got a hold of a microprocessor instruction set description and go, oh, I can understand this. And then I went back to the PDP-10 and I could understand that. But anyhow, the 8-bit microprocessor had 40 instructions, really simple to understand. The R64 has 2,000 instructions. And those are the main instructions. Each has variations. So, your instruction selection becomes like, this is where Godbolt comes in. Because I write little pieces of code, I run it through Godbolt, and it puts out an instruction. And it puts the bit pattern for the instruction and mnemonic for it. Well, it turns out that many of the mnemonics have multiple encoding with very different operands and things like that. So then, and this makes my eyes bleed doing it, is I look at the 32-bit bit pattern, break it up in the hex code, and then try to map it onto the instruction set, which is extremely tedious because nothing lines up on the byte boundaries. It's just a totally miserable process. It makes my eyes burn. So I've had to do a lot of that. As the CPUs progress, we got variations in the processors. One generation, the string instructions are the fastest way to do strings. The next generation, loops are faster, and then the generation after that, the string instructions are back on top. So all this is there are endlessly different ways of putting instructions together to get the same result. And if you read Agner Fogg's instructions on how to optimize code, you'll see that there are many variations. Some are faster than others. And of course, x87 is its own wacky universe. So that's really what the code generator looks like.
Is that generated by AI?
Well, I tried generating it with Grok and I didn't get a good picture. So I went to ChatGPT and generated that. So
Very good.
I don't know what motivated it to produce that.
I am curious what prompt you gave it.
Well, my secret prompt is draw a Gay and Wilson cartoon. That's what came out.
Okay.
Gay and Wilson is one of my favorite monster cartoonists. So, well, they don't actually look like Gay and Wilson's drawings, but I thought it was interesting enough. Loading a constant into a variable, you have two different instructions, and you have to make decisions. Is the right value coincidentally already in the correct register? Is it a common subexpression? Which is faster? Are multiple instructions needed? Is the effective address already in a register? The effect on the condition code flags all has to be taken into account. People always ask, when are you going to finish it? Everything changes constantly. Code generator author will never be unemployed except me, because I work for free, so I'm unemployed. But code generators are never finished, but the presentation is finished, so that's another AI generated picture. I love those AI generated pictures. I never have to worry about, is somebody gonna get mad at me if I use a picture? Just go straight.
If they do, you just blame the AI.
That's right.
So I spent my question that I saved for the end about debugging, so that's, but something that was not touched upon is one optimization that is the bane of people who write multi-threaded code, which is instruction reordering, barriers and all of that fun stuff that, you know.
Okay, back in the 90s, I wrote an instruction scheduler, which dramatically speeded up code on the Pentium and then the Pentium Pro
Reordering.
by reordering instructions. And it was based on an algorithm invented by Steve Russell. And the later versions of the CPU made that reordering thing obsolete, so it's been abandoned.
What was driving it? Avoiding cache spillouts or taking advantage of the pipeline that does.
It was the pipelines. Yeah, the Pentium has two pipelines and the Pentium Pro has 3 pipelines. And so the scheduler would read the instructions and would poke them into the pipelines and then would merge them back together again. So it was quite effective on the Pentium Pro and Pentium, but it produced nothing.
These days it's so
after it.
okay.
And you're right about debugging it is the nightmare. So there was the compiler switch to disable the scheduler. And then you could debug it and there was more of a one-to-one mapping.
You have to have, if you're going that route, you have to introspect somehow into mutexes and aliasing and all of those fun things, right?
Aliasing is okay. The schedule paid no attention to shared problems. Okay, if you're doing shared code, you need to use mutexes properly, and that's a whole other way of programming. The scheduler that I work with did not address that because nobody at the time understood how to write shared code.
No, I misspoke when I said mutexes, and I was thinking about spinning locks, right? Where you do the interlock exchange compare pattern, and you have a way of specifying memory, right? If it's set a barrier, so all of the instructions above this point don't get reordered, or everything below this doesn't get reordered, or both, right? Or I don't care.
You're asking how I deal with that? I don't.
You don't care about that.
Yeah, if you want to write that stuff, if you want to write a spin lock or something, your best approach is to use the inline assembler, which is very easy to use, and you can get exactly what you want with the inline assembler. And I think the compilers I've written have a really excellent inline assembler, very easy to use. It uses the same mnemonics as in the Intel manuals. So you don't. There was this movie a long time ago made in the 60s about this guy who was researcher who was given glasses that turned everything upside down. And for days he was, blundering around the house going the wrong way. And then suddenly wake up and everything was right side up. And,
that was an actual psychology experiment.
Yeah. And then they took the glasses off and everything was upside down again, which apparently caused him a lot of headaches and everything. But anyhow, the way GCC puts the operands, they're backwards. And so every time I'm looking at the GCC dump, my brain hurts because everything is backwards to me. And I don't want to get used to it because then.
Yes.
But anyhow, the inline assembler is really nice and you can embed it. It knows about variables. If you give it variable names, it can find variables on that. So anyhow, it's really, you only need a few places where you need to put spin locks in or whatever. So it's not a burden to do that. And the G programming language inherited all the inline assembler goodies on it. So now it turns out that very, very little inline assembler is actually necessary. Very, very little. So that makes it not as useful as I originally thought it was, but back in the olden days, it was pretty useful.
You also have the MMX stuff. You do vectorization.
It does not do auto vectorization because I view auto vectorization as an abomination. Because what auto vectorization does is it looks at your code and tries to reconstruct a higher level view of it. And my view is, isn't that completely backwards? You should be writing the higher level view and the compiler generates MMX code for it. So, to me, that's the correct approach. The auto vectorization is a horrific kludge when in actuality, the language should be fixed.
We use something like, or C++ Agner Fog has a thing, vector class, and you use those abstractions. You write your code using that. And
In other words, you're writing at a higher level.
Yeah.
You're not writing low level loops that you expect the auto vectorization to turn into high level. And, you know, I bought a book on how that's done, the auto vectorization. I read it and go, this is just interesting, but completely the wrong way to design things. So that's my annoying opinion on that. Unconventional. So, more questions. Who's going to run off and write a code generator now that you're all inspired?
So I've got a question.
Okay.
Just how different is writing a code generator for ARM than the x86? You said they were orthogonal. What's some idea of the kinds of things you have to do differently?
The biggest problem was dealing with the effective address, because there's no concept of an effective address in the Arch64. So what I finally had to do was disentangle the effective address calculations and have a fork in the code. So I can't explain it exactly. Like I had one function to do all the effective address calculations and the addressing modes, and that's split up into a bunch of functions now. So that's kind of the gist of it.
It had like, oh, sorry, go ahead.
No, and there are parts in the compiler that appear to be redundant, doing the same thing over and over again, and those kind of concern me. I need to figure out how to consolidate them. I need to figure out how to merge them properly. So the code generator for the ARM64 is only half done. And I abandoned any effort to do the ARM32 because I spend a year writing a code generator for obsolete CPU. Complete waste of time. The fun thing though is I actually have gotten programs from, the code generator has been able to generate simple programs that run on the Raspberry Pi. It's kind of fun. I have a Raspberry Pi and I just hooked it up to my network. I do a remote login into it and it's cool. And the whole thing.
Everybody has one of those, right?
Well, I got one as a conference swag thing, like about 10 years ago or maybe more, and put it in a drawer. I have no use for it. And I'm looking, I need to build an ARM code generator. What CPU is on that Raspberry Pi? An ARM64. I go, oh, the beauty of the ARM64 was in the setup in it. Because it doesn't come with the operating system. You have to download the operating system and you have your pick of operating systems. And I thought, oh no, this is going to be hell. Because the instructions are going to be wrong and incomplete and a lot of guesswork. So I carefully followed the instructions to the letter and it worked perfectly. I thought, at last, it works perfectly. I followed the instructions and it actually worked. It's a miracle,
Here's a question for you. You may not have looked at this yet. You looked at the RISC-V or RISC-V instruction set yet? Okay.
I know it exists, and that's the beginning and end of my knowledge.
Okay.
I did look at that. What was that Intel thing? They're super advanced.
Titanium?
Titanium, yeah. I looked at the
Oh,
instruction set and I thought, I'm not writing a code generator for this.
It's been dead for a long time.
I know, but when it was fresh
Oh,
coming thing, I was going, oh. But when I looked at it, I couldn't make heads or tails of how it was supposed to work and just not gonna do. So it's kind of nice to see the convergence of CPU types. Makes my life a lot easier.
Yeah, I used to do assembly back in the day, when there was MIPS and alpha, and those processors were really nice, like the instruction set was very uniform, and it seems like we just went down the wrong path, or just like Intel just never. I mean, it was always been popular and always had to keep compatibility, and so it's just been this mess, right? And the same thing with the.
Also, complexity comes from all the extensions that come one after the other. They try to find a bit pattern that doesn't make sense, and then they use that to extend the instruction set. That's why it's such a mess.
Look at the old 8088 or whatever it was, where they have all these things that they thought were important that had like 1 byte instruction codes.
Yeah, the binary, the BCD instruction.
BCD and stuff. Yeah, right. And those things aren't important at all anymore, right?
Yeah, they finally, I think, with the 64-bit version, decided to reallocate those.
Oh, they did.
Yeah, if nobody uses the BCD instructions, we'll just abandon them and repurpose them.
So I saw that it's really hard to talk because there's an echo, and I hear myself like 2 seconds later after I say something. But like I saw that Intel is thinking about doing a new instruction set that's actually 3-register opcodes. So add would be like R1 equals R2 plus R3.
Right. The ARM is like that.
Yeah.
The ARM instruction set has this interesting constraint that every instruction has to fit in 32 bits, which means as they added extensions, then they added variations on the encodings, which resulted in this horrendous complexity of the encodings on it. So they kind of started out with the simple idea of everything's going to be orthogonal and everything's going to fit in 32 bits, and it turned into just as big a mess as the Intel one, just on a different axis.
The only one I've seen actually pulled that off pretty well for a while was the PIC instruction. PIC microprocessor. You start out only programming in assembly. They had like 32 assembly instructions or something, and a uniform register set and some other. And I haven't looked lately, but I suspect as they went through time, it got pretty messy. It was like an instruction set you could learn for assembler easily in like an afternoon.
Yeah, 40 instructions, right?
Yeah, it was like 32, 40 instructions, and they were orthogonal, right? You had a base, you had one operand, another operand. That was the end of it.
That is WebAssembly. Have you looked at it?
I haven't looked at WebAssembly.
It is ridiculously oversimplified.
Simplified?
Oversimplified. There's exactly it's WebAssembly, integers and floating point, 32 and 64-bit. The end. So everything that those folks over there were learning about how Rust is generating WebAssembly, it's all going down to a ridiculously small collection of stuff. The committees around WebAssembly have talked about, for example, introducing a native string type and some of that kinds of stuff.
Mhm.
But right now, as of 12 months ago when I last looked, all of that was still either experimental or optional for a given WebAssembly implementation. So it's not a bad place to start if you want to learn an assembly language.
Mhm.
But I imagine for the folks in this room, it's going to be like, oh my God, you can't do this, you can't do that, you can't do the other thing. Or it's going to be, I'm going to have to, create 27 instruction chains to do one 6-letter Intel 64-bit instruction.
Well, I was really lucky to learn assembly from microprocessors, which were so simple. And I kind of feel bad for modern people faced with this incredible complexity.
Come on, Walter, say it. Back in my day. Say it, just once.
Back in my day.
There we go. Meeting adjourned.
When I could actually design and build my own single board computer.
The Z80 was awesome.
I use a 6802.
802, yeah, that was good too.
16.
The Motorola.
Yeah. Eventually grew up to be the 68,000.
I did 68,000.
Oh, yeah.
I never did assembly on the 68,000, but that's what I moved into C.
Yeah, the General Machines came with that.
Amigas.
I
They
can't even
rule.
solder anymore. You look at the size of those parts, I can't even see them. I don't solder them.
You know, Walter, the parts have shrunk, but that might not be the whole. Speaking from experience myself,
Yeah.
I used to be able to, solder pretty small stuff. And about a decade ago, I started getting magnifiers. Now I've got a microscope on this end and one of the magnifiers on this end. I can go back and forth.
Well, the soldering I do now is the wiring on my old car because that still uses big fat wires and, like solder them up.
So really keeping track of the optimization, back to my pet peeve, the debugging, it's really a lossy, it's an inherently lossy
Yes,
process.
yes.
It's not that it's too hard, it's lossy by its nature.
It's turning the cow into a hamburger. That's the best. That's not my description. It's what other people have characterized it as, and that's exactly what it is. And there's just no
Like, even if at every step you kept track, like, yeah, this was defined
That's all
in this
been tried.
line on.
They write papers on it. And
Sometimes it works, right? There's the dwarf format that had like some sort of its own stack-based instruction to execute to figure out where something was, so you could show it in the debugger and simulate tracing,
Well-
even if it was.
Think of it this way, because I haven't done any of the code generation, but I've run into this a lot debugging into assembly.
Yeah.
I've done a couple of times, right? Just imagine you've got two relatively simple, lines of, say, C code, right?
Yeah.
Just, do some adding, do some more adding, right? And then you turn that over to the optimizer and it decides to reorganize things for memory efficiency, right? You no longer have two independent lines that you can even go back to, right? You've got a set of instructions where these two things, yeah, they're still independent, but the order that they appear in the assembly code has been blended for, so they can make use of all the execution units or whatever other optimization it feels like doing. And, the only thing I've ever found is turn off the optimizer, debug that.
the problem is when the optimizer breaks your code.
Well, but the thing is, though, you turn off the optimizer and you can still detect that, right? Because it's like the code works when it's unoptimized. The code doesn't work when it's optimized. Therefore, the problem is the optimizer.
Not
Oh,
necessarily.
really? Okay.
Not necessarily, because it may mask problems with, you have a stack overflow.
Oh, that's true. Yeah, you're right.
Put
Yeah.
things on the stack, it behaves differently.
Yeah. Hey, by the way, folks, we do have about 5 minutes. So
We have a question online and also we have a comment.
Yeah, I was gonna say a couple things like so like the hotspot compiler for Java actually does de-optimization. So like when you break into the debugger, you're normally running the optimized code and then it'll make an unoptimized version that you actually debug. So
that's entertaining.
kind of hides the problem though. Like if the optimizer is broken, you won't be able to find out. But
If you have like memory corruption, it can behave differently optimized and unoptimized, and it doesn't mean there's a bug in the
Yeah, that's true too.
Or you could have an uninitialized variable you're relying on, or you could, return a pointer to the previous stack frame and optimize and unoptimize will give you different answers. So it's just a clue until you find it.
I remember some debug builds of compilers I used a long time ago would initialize everything to 0, but it wouldn't get initialized in the release builds. So a lot of times you'd be safe in the debug build because you were expecting a 0 value there, but you'd have effectively memory garbage, you'd be relying on it, and then it crashed in the optimizer.
Not a problem indeed, right? Because you
And then
You have to be intentional about it.
you have to, in D to uninitialize a variable, you initialize it with void. If you have no initializer, it'll default initialize it, and that pretty much ends the unless you use equal void, and then it's your problem. But when I debug problems like that, back in the C days, what I would often do is port the code to another computer or with a different CPU and operating system. And sometimes that would, especially for an uninitialized variable, it would help me identify where it was happening. Just because it lays everything out differently in the different machine. So there are all kinds of tricks like that to try to narrow down where the problem is.
I think Mike might have another comment.
Yeah, we should probably, let's do Mike's and then we should probably wrap up and.
So I was going to say that like I wrote a code generator a few years ago, and it's surprisingly similar to what you have with the like. I do the expression trees with the registers on demand and all that, and
Cool.
but like I'm starting to rewrite it, and I'm thinking more about doing like SSA, and just like going down the normal route. And have you thought about that?
Yeah, I thought about SSA until I realized that trees are the same as SSA. It just has a different word.
Yep. But they have like there's like standard algorithms for optimizations and register selection, and I mean I guess it's not true that they're standard, and it is all ad hoc, but
Well, the algorithms I use for optimization came from a course I took at Stanford in 1982, taught by Hennessy and Ullman.
mhm.
So I still have the notes from that class, and the whole optimizer and data flow analysis came from their presentations. And the fun thing about it, it was the first compiler for DOS that did data flow analysis, and it went for one of those benchmark roundups. And the benchmarks in those days was just a repeated x equals 3 inside of a loop. And the data flow said, well, that's a dead assignment, and deleted it. And the journalist who was writing the article said, oh, he wrote in his roundup that my compiler was buggy because it didn't generate any code for the benchmark. Our sales tanked for that quarter because of that. He never bothered to contact us and ask about it. And, after another semester, the other compiler vendors all started doing data flow analysis optimizations too, and they had to update all the benchmarks.
Yeah. Hey, folks, I am noticing the lights blinking outside, which I think is a hint to us to
All right.
depart the premises. Thanks, everyone.
Yes.
Thank you very much.
I can continue chatting, at least for those here in the room. Red Robin is down the street and some of us are heading there. Okay, thanks, folks.